In a previous video, I showed you how to find the number of triangles in an ambiguous case problem. And in this one, I'm going to talk about solving the ambiguous case, specifically with two triangles. If you got 0 triangles, you just simply state that it's 0 triangles and move on to the next problem. If you're solving an ambiguous case with 1 triangle, you'll solve it like normal. If you need a reminder of how to do that, I do have videos on using law of sines that you can go back and watch. But with 2 triangles, it's a little bit different. So before we delve into this, let's go ahead and quickly remind ourselves what a 2-triangle case looks like. So remember, this only applies to SSA triangles. So if you have a side angle pair and then a loner side, that's when you know that you're going to be using ambiguous case ideas. In the previous video, we already discovered that this is a 2-triangle case. If you want more proof, I'm going to go ahead and go to that GeoGebra application that I made previously, where I've already inputted this information. So you can see my angle A is 55 degrees, my side length A is 30 units, and then my side length B is 34 units. This creates 2 triangles because you can see one triangle here, and as I swing the arm across, you can see a second triangle is formed right there. So this is a quick little visual proof that this is in fact 2 triangles. I am going to come back to this image later, but for now we can go ahead and agree that this is going to create 2 triangles. So let's see the setup for this. Normally, if I was solving a triangle, I would create a little table so that I have all of the information nice, neat, and organized, where I have angles and then I've got my side lengths. But now I've got 2 triangles that I'm dealing with. So I actually have to write this table a second time. And you can't just leave them as ABC and ABC, because you, as somebody who's solving the problem, and anybody else who's looking back at the problem, needs to be able to identify between the first and the second triangle. So I will call them A sub 1, B sub 1, C sub 1, and then I'll do A sub 2, A sub 3, A sub 2. Decided to start counting there. And 2's for all of those as well. So you're going to hear me abbreviate it. Instead of saying A sub 1, I'm just going to start saying A1 and A2 and all that. Now the good news with this is they still give us certain information. They have told us, and we cannot change the fact, that angle A is 55 degrees. And that's going to hold true for both triangles. So this given information will always stay the same. So this side length A1 will also be 30 units, A2 will be 30 units, and it will stay that way. B is going to be 34 on both triangles. It's the matter of solving these triangles that's going to be a little bit more difficult. So let's go ahead and take a moment and put a pin in this. We'll come back to this, but I want to show you what we're going to be doing. So on here, what I would normally do is I would draw this onto my board, I would copy it, and then I'd swing this over and I would copy this image as well, and I'd overlay them on top of each other. To make my life a little bit easier, I have already done that on the next slide. So what you're going to see is, I believe it's in white, you'll see this triangle, and then in yellow, you'll see this triangle. And we're going to label some stuff to kind of help some of those visual folks. So here is all that information. We've got in white that outside triangle, and then in yellow the inside triangle. And as we said on the previous slide, this angle is always going to be A. On both triangles, this angle is going to be A. And then on both triangles, this side length is going to be B. And here's where it gets a little bit different. This is side length A, specifically on the first triangle. This is side length A, specifically on the second triangle. Now these are the same value, but you'll see they're located in different spots. So this angle here is going to be angle B1, and then this angle here is going to be C1, which means that this side length here is going to be side length C1. So our white triangle is fully outlined. Our yellow triangle now, we're going to have to go ahead and also outline that. This is angle B2. This little angle right here is going to be angle C2. And then everything else is already, oh, excuse me, we need to do this side length here. This little teeny tiny one is C2. So it's a little bit confusing, but this image is going to help us with our proof of why it works for those ambiguous case triangles. So I'm going to go back to my little chart here, and you can see that we actually have the ability to solve for angle B1 here. So we would use our law of sines and solve for B1, and the way we would do that is by doing the sine of B1 over little b1 is equal to the sine of our side angle pair, a1 over little a1. Do a little bit of rearranging to get that, sine of angle b1 is equal to b1 times the sine of a1 over little a1. I am going to scoot this down just a little bit so that we have room to see things. So now we're going to plug in values, and we're going to solve this on the calculator. Just like always, our units are in degrees, so before I enter anything on the calculator, I'm going to be careful to make sure that my mode is set to degrees. Sine of 55 degrees divided by a1, which is 30. So punching all this into my calculator, and I'm going to go ahead and assume that you're relatively experienced with the law of sine, and that you're going to take the inverse sine. But when it's all said and done, for our angle B1, we should end up with, give me a moment to plug this into my calculator, you should be following along as well. I find that a lot of students have issues plugging into their calculator, and they end up making silly mistakes. So I find out that my angle B1 is 68.182 degrees. So when I write it down, I like to write to the third decimal place, but if I'm ever going to use this angle again, I'm going to make sure to use the whole length of it. So I'm going to round to 3 decimal places, but if I use this angle again, I'm going to use the 68.1, and I'll go ahead and write this down. 68.18249,401, just to make sure that I don't end up having a rounding error as I go through. So what we've done is we've discovered angle B1, and this is just solving it like normal. If you notice on our picture, this right here is angle B1. We just discovered it's 68 point blah 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 blah. Inside of here is actually a third hidden triangle. This is not a solution to the problem. This that I'm outlining in green is not, green is a bad color because it's right next to that yellow. We'll use blue. This triangle in blue is not a solution to the problem. It does not have our given information, but this is going to help us solve everything else. This is an isosceles triangle. We've already stated that A1 and A2 are the same. They are both 30 units long. So what that means is this angle has to be the same as this angle here. This also has to be B1. When you look at triangles, the side length that is opposite of the angle, if you've got 2 same side lengths, remember your isosceles triangles, if you've got 2 same side lengths, then those opposite angles will also be equivalent. And that's the key to solving these types of problems. You'll notice these 2 angles together make up 180 degrees. So if I take 180 degrees and I subtract B1, I should end up with my length of B2. So let's go ahead and go back and do that. So I'm going to go back to this page here, and I'm going to say I'm going to write this in blue, that B2 is equivalent to 180 degrees minus B1. So if you remember, this actually means that they would be supplementary angles. So two angles that add up to 180 would be supplementary angles. And that's what this ends up being, is B1 and B2 are supplementary angles that add up to 180. So again, I'm going to use that whole shebang in my calculator. If you know how to store values, that might be a beneficial thing. So we have now discovered that B2 is equivalent to 111.81. I'm going to write out the whole thing. So I can come over here and say that angle B2 is 111.818. I'm going to go ahead and round that number. And there you have it. We now have two separate triangles that we can solve completely separately from each other. So what I think about is these are two totally separate problems with a bridge between them. So everything is totally separate except for when you cross this little bridge. The first angle you solve for, I call the linking angle. It links the two triangles together, and it's always going to be the first angle you solve for. So this right here allows the information to flow from one to the other, and once you solve this side here, you will treat them as two totally separate triangles. So now that I have this information and I've done my linking angle, I can totally ignore the second part for now. So to help me remember that I'm going to ignore it, I'm going to just scratch it all out here, and I'm going to totally ignore it until I absolutely need to look at it. So to give myself a little bit more space, I'm going to go ahead and scroll down again. I need to find angle C1. Well, I know every single triangle in the whole wide world adds up to 180 degrees for those interior angles, which means, I'm going to switch colors again, C1 is going to be equivalent to 180 degrees minus A1 minus B1. Again, I'm going to use those whole numbers there. I am not going to use rounded values because rounded numbers give rounded answers. So angle C1, once you plug it into your calculator, will be 56.8175. My board freaked out on me a little bit. 75059 degrees. So with rounding, it'll end up as 56.818 degrees. Now again, we're left at a position where we could use law of sines or law of cosines. I find it easier personally to use law of cosines, so I'm going to go ahead and do that. To get side length C1, it's going to be C1 squared is equal to A1 squared plus B1 squared minus 2AB cosine of C1. And this comes from our law of cosines. If you've forgotten how to do that, you can go ahead and look back at my law of cosines videos. So it's equal to the square root of all the stuff when you plug in those numbers. 30 and 34 are our values. So part of the reason that I'm using law of cosines is because it's nicer numbers. I don't want to have to use all those decimal places, even though some students find the law of sines to be a little bit easier. Here I can pretty much guarantee I only have one big long nasty number, and that is my 56.817, all that. And again, when I plug it into the calculator, I'm going to use all these digits, but right now I'm just kind of simplifying through it. So plugging it all into the calculator, you end up with a value of 30.65114399. This is a very long, disgusting number, but we are not going to use that as our answer. I'm just going to round to 3 decimal places, so 30.651. 30.651. 30.651. The very last thing I'm going to do is check to make sure that my answer makes sense. So I've got the smallest angle here with the smallest side. I've got the medium angle here with the medium side. And you'll notice that these two angles are very, very close, and these two side lengths are very, very close. That tells me that I'm also probably on the right track. Last but not least, I've got largest angle with the largest side. Now that I've solved this triangle completely, I'm going to go ahead and not ignore the rest of this side. I will follow the exact same procedure, so I encourage you to try and beat me to the answer this time. I'm going to start with 180 degrees. So C2 is equal to 180 degrees minus A2 minus B2. Again, I'm going to use those whole values as I go through. So 180 degrees minus 55 minus this angle of 111 using the whole shebang gives me a C2 angle of 13.182494 degrees. I'm going to round to the third decimal place and get 13.182 degrees. Which brings us to the very last bit. Last problem, I used the law of cosines, so I'll go ahead and use the law of sines here just to mix it up a little bit. The law of sines says the sine of angle A2 divided by side length A2 is equivalent to the sine of angle C2 divided by side length C2. A little bit of rearranging here tells me that C2 is equivalent to A2 times the sine of C2 divided by the sine of A2. Now we're going to plug in our values, and we'll get A2 of 30, the sine of angle C2, which is 13.182 degrees. Again, I've written 182, but I'm going to use this whole value here. Divided by the sine of 55 degrees, giving us a final answer when we plug it into the calculator, 30 times the sine of that big nasty angle, divided by the sine of 55. Our C2 is 8.352053670. Oh, that's what I get for not looking at the board. 352, it looks like my board also doesn't want me to say out all these values. So again, I'm going to round to those third decimal, 8.352. Very last thing I'm going to do again is double check smallest angle, smallest side, medium angle, medium side, largest angle, largest side. So that is the key there. The idea is your linking angle is the first angle that you solve for. And when you do that, you're going to do 180 degrees minus that linking angle, all because of this picture right here. These guys right here are supplementary angles. So let's go ahead and take a look at our first practice problem. Here is our first practice problem. I'm going to go ahead and tell you it is a two triangle problem. I've selected two practice problems specifically so that they will be two triangle problems. I'm going to start by going ahead and writing my little chart here, A1, B1, C1, and then A1, B1, C1, followed by my second triangle, A2, B2, C2, and A2, B2, C2. Now what I'm going to do is encourage you, just like always, to pause the video and try and beat me to the answer. So hopefully you have tried out this problem, and hopefully what you did is start by writing out the given values. If you notice, I gave you angle B this time, so that may have tripped you up. But all of these given values will stay the same across both triangles. So I know these values are 100% going to be 47, 8, and 10. And the way I solve this is starting it just like it was any other problem. I'm going to totally ignore this second triangle temporarily. If I was ignoring that triangle, I would solve this to get angle C1. I would use law of sines. So the sine of angle B1 divided by side length B1 is equivalent to the sine of angle C1 divided by side length C1. Doing a little bit of rearranging. Again, I'm going to trust that you have practiced law of sines enough to be able to get these rearranged. Sine of B1 divided by B1. And we're going to plug in our values. So C1 is 10, sine of angle 47 divided by side length 8. To get angle C1, don't forget whatever this is, you take the inverse sine of that, and you should be in degree mode. So 10 sine of 47 divided by 8, and then taking the inverse sine of that gives me an angle of 66.091, 25, blah, 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 blah. Again, whenever I'm using this value, I'll use the whole shebang, but for the sake of time and your sanity and my sanity, I'm going to do a little bit of rounding here. This is my linking angle. This is what's going to allow me to link these two problems. And I actually do separate these entirely. So I've got my little line here separating these. I'm going to use my linking angle to figure out what angle B1 is, C2 is going to be. So C2 is equal to 180 degrees minus angle C1. This is my linking angle. It's always the first angle you solve for on a two-triangle ambiguous case. So we end up discovering that this angle is 113.9087 blah 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 blah. Again, use that whole value. Here is my little bridge between them, allowing that little piece of information to flow. 113.909 in terms of rounding. And again, mentally, I am going to totally ignore this triangle. I do not care about it until I'm finished with triangle 1. With triangle 1, I can find angle A1 using the 180 degrees idea. So A1, I had the larger setting on, is equal to 180 degrees minus B1 minus C1. So angle A1 is going to be equal to 180 minus 47 minus the 66, giving us another angle of 66.9087 blah 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 blah. So we end up with 66.909 degrees. Let's go ahead and I'm going to use law of cosines because I really do think it's a little bit easier to solve for that last side length. So a squared equals b squared plus c squared minus 2bc cosine of a. And all of these are specifically triangle 1. Plugging in those values and taking the square root, we're going to find that A1 is equivalent to, and I'm just going to go ahead and plug these values into my calculator, 8 squared plus 10 squared, I'll write it down, plus 10 squared minus 2 times 8 times 10 times the cosine of that 66.9087 blah 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 blah. And when I plug it into my calculator, again, I'm going to make sure to use all those values. Don't forget you end up having to take the square root. So I left off my squared there. You'll discover A1 is equivalent to 10.0622 blah 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 blah. So 10.062 is my rounded answer. 062 is my rounded answer. Again, looking at these, I see these two angles are very, very similar. It will not always work out that way, but it's just something that's happened in these past two problems. These two side lengths are very similar, but the larger side length does have the larger angle along with it, and the smallest side length is the smallest angle. Let's go ahead and finish this up. We've got a little bit more left on this problem. We need to switch over to the second triangle. We'll use the same idea of 180 degrees minus B2 minus C2 is equivalent to angle A2. So 180 degrees minus 47 minus the 113 gives us angle A of 19.09125 blah 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 blah. So there is my angle A2, 19.091 degrees. Again, I'll use law of sines just to mix it up a little bit to solve for that side length A2. The sine of, excuse me, I like switching colors here so that it is very obvious what I'm solving for. Sine of A2 divided by side length A2 equals the sine of, keep in mind I've got a choice between my side angle pairs. B2 is not only nicer, but it's also given information. So isolating A2, that's equal to B2 sine of angle A2 divided by the sine of angle B2, giving us an actual value 8 times the sine of 19.09 blah blah blah, running out of space, divided by the sine of our given angle, 47 degrees. 8 times the sine of that angle divided by the sine of 47 gives us a side length of 3.5777, so on and so forth, which rounds to 3.578. And there you have it. There is how you solve for a two-triangle problem. It's really the same thing. You're just solving two separate triangles. It's this linking angle that allows you to solve those differently. So this linking angle is the first angle you will solve for, and you're going to find out that these are supplementary angles. And again, that comes from this picture right here, supplementary angles. I hope that helps you in solving two triangles. And again, if you do need practice finding out which triangle or how many triangles there are, take a look at my previous video for assistance with that.